Hi folks, I hope this finds you doing well and you're healthy and safe. In this video, I would like to show some enhancements to Illuminated Cloud's log analyzer, specifically enhancements around profiling and even more specifically around hotspot identification and characterization. And if you're not familiar with what that means, I'll explain it as we go through the demo. Ever since it was introduced, the log analyzer, which was a follow-on to the log viewer, the more simple log viewer, has had profiling capabilities. It's given you the ability to see how much of certain given resources, governor limited resources, are consumed at an aggregate level and at an atomic level, specifically in a particular execution unit like a method body. And it has allowed you to do that for things like duration, heap allocation, database metrics like the number of queries executed, the number of rows returned, the number of DML statements, the number of DML rows, things like that. It could still be a little bit of a burden to find exactly where resources are being consumed, especially if you're contending with something like a resource overflow, like a too many SQL queries executed or a CPU time limit exceeded or too many DML statements. Those can always be a pain in this governor limited environment of Salesforce development. And so I'm hoping that the tools I'm about to show, some enhancements, some new features, will make great strides in at least allowing you to characterize what's going on, where resources are being consumed, what's driving their consumption, and ultimately open up strategies for how you can refactor your code, restructure your code in order to better use the governor limited resources. This is the type of thing that is best illustrated by example, by demonstration, rather than by elaboration or discussion. So let's just go ahead and dive in. As always, these are going to be driven by logs that are executed with a sufficiently high logging level. Illuminated Cloud comes with various presets. Unless you get a truncated log, I recommend when you need to profile that you run with the highest logging level, which effectively sets everything to finest. I'm going to go ahead and do that in a unit test right now for convenience, but if you were profiling an external process, you would just need to set up the logging levels using Illuminated Cloud or whatever your favorite tool is in order to crank things up that high, execute the process, and then load the log into Illuminated Cloud. So let me go ahead and run this particular unit test for profiling. And as soon as it executes, I'll show you first the enhancements, and then I'll show you some of the brand new features that are going to facilitate hotspot identification and characterization. Okay, so this opened automatically because I ran it for profiling in a view that allows you to do CPU time and memory profiling, basically time and space. And so what you would traditionally have to do, and it's a bit onerous, is you'd have to start drilling in and try to figure out where these resources are being consumed. And so we can see that the total test execution time was 517 milliseconds, and it used almost 60K of heap. We can also see that the execution of the test itself, this particular method, only took 2 milliseconds. And what that means is the other 515 milliseconds, that was all consumed by the transitive execution of these methods that are in the body of that method. So self-time really means statements that are not method invocations, not constructor invocations, that don't result in triggers, things like that, that are happening in the current context. Similar with the heap utilization. And so what you would typically have to do is drill down until you start to see the self meet the total, meet the total amount consumed, and then you actually know that you've reached a point where resource has truly been consumed. Again, this could be an onerous process of drilling down. There's now a new action over here called Smart Expand. And if you click it, what it does is it automatically expands that view to the point where further expansion is not going to yield new insights given the type of profiling you're trying to do in that view. So in this case, for CPU time and memory profiling, it's going to expand until the self duration and the total duration match, and or the self heap and total heap match, depending upon whether those are present in the same method. And so let's take a look at an example of this. It stopped expanding this particular node here because the total duration transitively for this method was 6 milliseconds, and it itself took 6 milliseconds. There's no further information to be gained on execution time, and similar on memory utilization. Let's move over to a different view so we can actually see another example of that. So we're going to move from duration and heap profiling to database profiling. Now this is one of the other enhancements that's come in with this particular release, and that is the way that the information is conveyed for database metrics. Previously, it would only show the total metric until you drill down and there was a self metric, and it would swap in the self metric for each of these columns. turned out that that was lossy because you could have a situation where you could have a DML statement execute, and then you could have another one execute transitively because that DML statement caused a trigger to run, which then did post-trigger DML on other objects or even the same objects to touch them up, and you would lose that information. Now this actually shows, excuse me, the ratio of self-consumption to total or transitive consumption, and then that relative to the governor limit of that particular resource in that code unit. And of course, that may vary as you drill down. For example, if it goes from being a standard process to being an asynchronous process, or if it's already an asynchronous process, you can have higher limits in async. And of course, in a unit test, async runs synchronously whenever the test completes or when you call test.stop test. So you may see the right-hand side change, but the point is all the information that you need is conveyed here. And now we can go ahead and smart expand, and we can get down to where we can see very clearly where the individual resource consumption is happening. And in this case, we're seeing kind of death by 1,000 paper cuts, and we'll actually dive into that later as we're doing further analysis. So if we scroll up, we can see some DML statements and DML rows occur here as well. Yeah, there's some right there. So you can see that the Smart Expand automatically expanded the tree. So now all you have to do is peruse the tree and you can see where the resources were consumed. So that's the second enhancement. I'm sorry, the second enhancement is the better presentation. The first enhancement is the Smart Expand. Now let's take a look at the third enhancement to existing functionality. We go into the hotspot identification view, the cumulative profiling and resource analysis view. And if you're not familiar with what this is, the original log, when run for sufficiently high levels of profiling information, will actually add a section at the end that shows effectively aggregate information about query execution, about DML statement execution, and about your most expensive methods. So we can see here the queries that were run. So we can see on this line, this query was run 96 times for a total of 209 milliseconds. Similar down here with DML, and we can see some of our more expensive actual methods in composite. And Illuminated Cloud has always included those at the bottom of the log whenever you change to this view and you've run with sufficiently high logging levels to capture this information. Now, what I discovered when I was implementing the features that I'm going to show in just a moment, the new features, I found that the log wasn't always accurate with these conveyed cumulative aggregate values. And I found, for example, that it showed that this query had executed 15 times when I knew that it had only executed once. And I didn't understand that. I didn't know if it was trying to convey that this loop had actually executed 15 times. It didn't. It only executed 6 times. There were only 6 users, plus basically a halting iteration to decide that it had drained the result set. So I found that this was an incorrect number, and I actually found this in a few different places. And so what that drove me to do, because the last thing you want to do when you're trying to arrive at rational and accurate conclusions about where your resources are being consumed, is use inaccurate inputs, inaccurate information. So what I did is I instrumented Illuminated Cloud to actually count these same metrics up in aggregate and present them as well. So whereas previously we had count and duration only, and those were what were reported from the log, now we actually have reported versions of those, and we also have, excuse me, observed versions of those. And I'm actually showing both because there are actually conclusions you can reach by combining the two. And I'm going to show some examples of that in just a moment, where Illuminated Cloud may see things that the log itself doesn't convey, at least in its cumulative profiling section, and vice versa. The duration actually doesn't vary much. You can see there's a 1 millisecond difference here, 1 millisecond difference here. For the most part, you're not going to see much variability there. It's really in the counts, in the invocation counts. I also found that the method invocations were very accurate. There was no reason to actually do observed counts there. So that's why you see effectively an empty column here. Let's go to another project that actually exemplifies this more extensively. So this is Doug Iyer's Mass Action Scheduler. I have 2 projects I'm going to use in this demo that are larger in scope than my demo project and can convey some more interesting information and show some more interesting use cases. So in this one, I went to the cumulative profiling section, and we can see the same type of behavior that we just saw. We can see that a static query was used as the right-hand side of a for each, basically the iteration collection. And that's the same thing we saw before. And so at first I thought maybe that's what it was. And you can see several instances of that. Here's another one, and here's another one. But here's another one that there's a mismatch between reported and observed. And the main thing it has in common, this is just passing in the results of a static query as a call argument, an invocation argument of a method invocation. And so the conclusion I've reached at this point is anytime that you use the results of a static query without assigning it first to a variable, you basically inline the usage of it, you can have this type of a disparity in the aggregate report. Now, I've already told Salesforce about this. I'm sure that it's something that'll be resolved. And if it gets resolved properly quickly, then perhaps the observed can go away. But let's take a look at some of the other information we're getting from observed. Here's a situation where we see a DML operation that Illuminated Cloud saw in the log because there was actually a DML event, but that was not conveyed in the aggregate section of the log at the end. And I'm not sure why that's the case. This happened indirectly when test stop test was called, and it went and effectively ran what would have otherwise been asynchronous behavior, but so were some of these other rows. So that actually doesn't hold consistently. And conversely, here is a query that was reported that was not picked up because there was no corresponding query event. And the reason is that this is not a static query, and it's not a dynamic query by calling one of the database.query variants. Instead, it is calling eventbus.getOperationID. So one thing I've also done is reached out to Salesforce to ask what other system APIs get included from an accounting standpoint as either queries or DML, aside from the methods on the system database class that correspond to queries and DML, so that I can actually have Illuminated Cloud properly account for those, because I don't know if this actually happened 6 times or if this is another inflated value. Anyway, the point is that Illuminated Cloud is giving you the full picture, what the log said in its aggregate at the end, and what the log said as events fired, and Illuminated Cloud processed those events in order to effectively draw the tree that we're using for this type of analysis. Okay, so now what I want to do is I want to demonstrate some of the new features. So why don't we go ahead and move back over to this project, and let's go through some of the use cases, the brand new features. Let's start with this, because this does represent something certainly anomalous in the log, or at least potentially incorrect. And let's show that it is in fact incorrect. I'm going to use a new feature called show callers. If you've used traditional first-class dedicated profiling tools, my favorite for Java is called Yorkit, then you're probably familiar with these terms: callers or backtrace analysis, callee analysis, and merge callee analysis. I'm going to go through each one in turn. I'm going to talk about why you'd want to use each one, and they're not mutually exclusive. You actually use them in combination in order to understand resource utilization. But effectively, when I say show callers, I can do this on any particular line of code, any method, whatever I want from the log. I'm just using the aggregate here. It's going to take that line of code and it's going to figure out what was the code path that led, or code path or multiple code paths that actually led to the execution of that particular line. And so we can see the line of code where that query ran, and we can see that that was invoked right here, and we can see that that in turn was invoked right here, and we can more importantly see that it was invoked exactly once in terms of the information conveyed through the log. So we can see that there were not 15 actual invocations. We can see that there were not even 6, corresponding to the number of rows, that query ran exactly once. Okay, so that's caller. Let's look at a more interesting example of a caller. Let's take a look at this. Now, I instrumented this particular test to fail by overrunning a governor limited resource, in this case, the number of SOQL queries that can be executed. As you can see, it says that there were 101 SOQL queries, and of course, you're only allowed to have 100 in a traditional process. Again, that's a forced failure. This is going to be a more simplistic example than what you're probably going to fight with in real life, but let's take a look at how you can use this tool in order to try to figure out how this happened, why this happened, and what you might do about it. So I'm going to right click and say show callers. How do we end up running 96 queries? And it's going to show all the code paths that got us there. So we can see that this line represents 96 queries. We can also see that it was invoked 96 times. So basically a one-to-one correspondence between invocation and query. So minimally, that's starting to hint that some form of bulkification or batching is going to help us there. Moving down the call stack, we can see that not only that, but this was specifically called from within a loop. Again, we know that DML or queries executed within a loop generally is an anti-pattern and needs to be bulkified. Moving up again, well, now we see we have branching logic. We got here through 3 different disparate paths, and we can see that we got here with 20 here, and we can see where we actually did 20 iterations. We got through 30 here, and we got here with specifically 30. And here we got here with, well, we've got 51 were requested and 46. So what I can conclude is that it ran 45 successfully, and then the 46 caused the test to fail. And of course, the other 5 were not allowed to run. And that's what led us to our 101 out of 100 that were allowed. But more importantly, this is how we got to 96. And if I wanted to see all the code paths, you can see all these started with the test and basically different paths of getting to the same ultimate place that used that resource. So again, it's a simple example, but you can see in this case that we can do what I would call bottom-up analysis. We found a place where a resource was heavily consumed right there. And I want to know, how did we get there? And based on how we got there, are there opportunities for immediate optimization? We saw loops. We saw that there's a one-to-one correspondence between queries and invocations, things like that. And that screams certain invocation pattern or certain optimization patterns in Salesforce. Okay, so let's take a look at another way we can do hotspot analysis, because we got here by starting with this cumulative profiling information, but there's another way that we can do the same thing. Let's just go to our test that's having issues, and let's say show callees. Now, callees, what this means is it's going to take this test and find every method, every constructor, every trigger that was invoked, and it's going to go and analyze its resource consumption, both total, transitive, and self for the given resources. But you can see that things don't actually add up. They don't total up to 100% here. And the reason is there's overlap here. Again, this is a flattened list. Some of these things call the others. We're going to look at a way to see things through more of an invocation stack in just a moment. But with callees, it's a flat list. And the idea is that we're looking for long polls. We're looking for the most egregious offenders. So if we go back over here and look at database analysis, and another feature that's been added here is in these views, you can sort. You can sort by these columns because you're looking at things in aggregate. If we go back to the original log, notice I'm clicking on the top here on the header. I can't sort. And the reason is this is a hierarchical view, effectively a graphical view of this information from the log. Excuse me. And that view and this log, the vertical axis is time. As you move down through the log, you're watching things execute in sequential order. Sorting by that would not make any sense. But once you get to these aggregate views, it makes total sense to sort, because what you're looking for are worst offenders or most expensive operations in that category for that metric. So in this case, we can see that 96 queries ran explicitly here because this is our self column. And now we can, even though we're not in the original log view, we can see callers from here and get back to that same view that we saw from the cumulative profiling view. So there's a couple of different ways to find your hotspots, to find your areas of most heavy concentration when using a resource. So now we have this, and we already analyzed this. So let's take a look at another example. Let's move back over here, and now let's take a look at CPU time and memory analysis. And what I want to see is, of these 517 milliseconds, where did that time go? So I can say merged callees. And this looks more like the original log, but again, the vertical axis isn't time. We can go over here and say, where was our time spent? Well, if I sort by self descending, it's not terribly useful because I need to do drill in to find things. So let's go ahead and sort by total duration, and let's figure out where the actual time was spent. So we can see that of this, 30% was spent here, and 29% was spent here. Once again, we can use our smart expand, and we can get down to the point where things are no longer interesting, and we can see that this is the place where the majority of that time was spent. And so we can actually see that. One thing I want to show, I wasn't paying attention when I did it, is I only expanded this one node. If I expand click the top of the tree, I can expand the entire tree. But very importantly, if you only want to know about a particular branch of the tree, if you're focused on what happened under a branch, you can smart expand just that branch of the tree so that you don't have noise around it. So this allows us to basically see where the time was spent. And we can see that really things kind of stopped here from a duration standpoint, but not quite from a memory utilization standpoint. We have to get down to some of the transitive system calls that were made. Let's go look at another example of this again in a larger project. So in this case, we've moved over into Financial Force declarative lookup rollup summaries. I've already executed a test. Let's take a look at callees. And what we can see here is that we have a test that ran for about 6 seconds. So we're not quite in danger of running into the maximum execution time of 10 seconds. But certainly, we need to see if there are any long polls that could be addressed. And we can see by sorting by self that we have one that was about almost 70% of the total duration. So let's just go through a use case of what we would learn from looking at this. So if we examine this particular method, we can see that it's creating users. And we can see it's running one query, two queries. It's doing one DML, two DML. There are no loops. It looks pretty efficient to me. I don't know if there's a way to optimize this given that we have to create a user. And in reality, user creation is one of the most expensive things that you can do in Salesforce. So it's not entirely surprising that that's what we're seeing. Let's just change this over and look at database analysis. And we can see that same method. We can see that there were 4 queries run, which makes sense. There were 2 iterations, each ran 2 queries. And then we can see that there were 4 DML statements. Again, we can see that there were 2 DML statements, 2 invocations. That all bears out. So there's probably not a lot that we can do here. So let's go back over to our other view and see if there's a next worst offender. So going by duration self-descending, we can see that the next one was maybe 15%, not much. And if we look at it, we can basically see that there are no loops. It is not really doing a whole lot. I don't think there's much opportunity to improve that. And the reality is that this is probably what you're going to find very often. There are going to be 3 different things, or maybe more than 3, but 3 things that come to mind that you're going to end up trying to do as a result of the information you get from these tools. Once you understand using, we'll go back over here. Once you understand using callees or cumulative resource profiling where your hotspots are for that resource being consumed, then the next thing you have to do is try to understand, are there individual single places where that resource is being consumed heavily? And if so, are there any things that you can do about it? And the things that are going to help there are going to be caller analysis in particular, because you can see all the paths that led to it and see along that path, were there any opportunities for optimization? Or you can take a look at whether it needs to be moved out into async. For some of these governor limited resources, the best thing you can do is kick it off into another process if you don't need the answer immediately. It just depends upon whether that's acceptable for that use case. But if it's something that's happening more in aggregate, you can use merged callee analysis, and you can understand what the constituent pieces are that contribute to that resource consumption across that aggregate node that seems to be very heavily laden with it. Again, what you conclude from that is going to vary based upon the process, and you may find that you just have a lot of little pieces, and you either need to refactor, you need to break it into synchronous plus asynchronous, and hopefully there are a couple of opportunities for bulkification. But this tool allows you to find those insights and decide then what you can do with the information that you've found. I hope you found this useful. One other thing actually I wanted to show that I'm not sure a lot of people are aware of is, as you're doing this, obviously real estate is valuable because you want to be able to see as much information as you can. And you can actually take any of these tool windows, whether it's Log Analyzer, SQL Query, Anonymous Apex, or any of the IDE's tool windows, the Git tool window, and you can move them out into their own window. Now, by doing so, I've lost the connection to the source code. As I click on things, I don't see the source code. I can either split the current monitor into 2 windows, or I think a lot of people work with multiple monitors these days. You could put the tool window, the log analyzer on one screen, and then the actual source code on the other, and have a nice maximized view of each. But I didn't know if people were aware that you can actually do that, and I definitely wanted to show that. Okay, so that's what I wanted to demonstrate. If you find any bugs, let me know. This is a very complex set of enhancements and new features in terms of the way the paths are calculated, the way that aggregation takes place, the way that nodes are merged that should match one another, quite a bit of filtering of what would otherwise be noise. I think things have come out quite well. I've actually validated the computed aggregates pretty heavily. There's a chance that they're not perfect. I'm sure that there are bugs. You find them, let me know. The best thing that you can do is actually to send me a log that represents the issue, that reproduces the issue, so that I can just load it right here into the log analyzer. I may not have access to the backing source code, but I can see the behavior right here. Send that over to me. If you want to send it privately, feel free to do that. I understand logs can have sensitive information. Otherwise, thank you very much for your time, and I hope everyone stays safe. Bye.